In this task, we are required to calculate the pH for a strong acid. And with a strong acid, we can assume that the acid is entirely dissociated. So we have here, let's say, acid, and this totally dissociates into proton plus A minus. So this means that our proton concentration here is equal to the original concentration of the acid. We also have to take into account that water, when it dissociates, it also produces protons plus OH minus. We know that the proton concentration in pure water is 1 × 10⁻⁷ molar. And I will come back to that, why it is important. So we can do pH equals negative log of the proton concentration. And in this case, we said this proton concentration is made up of the concentration of the acid plus the proton concentration from the water. And I write it like that. So in our case here we have 6.61 × 10⁻⁵. So pH equals minus log of 6.61 × 10⁻⁵, and we need to have that in molar, plus 1 × 10⁻⁷. That is from the water, that's the concentration. And if we put that into a calculator, we get the pH of 4.18. So why is it important to take this proton concentration of the water into account? So let's have a look at this question here. So here we have a very dilute acid. And if we tried to just simply calculate the pH without the proton concentration, we would get total nonsense. But with the proton concentration, we could write pH equals negative log of the acid concentration plus the proton concentration from the water, and I write this again like this here. So we get equals minus log of 6.0 × 10⁻⁹ mole per liter plus 1 × 10⁻⁷ mole per liter. That's from the water. And if we put that into a calculator, we get 6.97. So not quite neutral, because we have an acid, but because the acid is so dilute, we really need to take the proton concentration into account.